Hello there, and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened. Because tonight, we're going to explore something truly amazing. We're going to imagine what it would be like to surf a gravity wave. Now, you might be thinking, waves are for surfing. Ocean waves, you can ride them, you can feel them. But what about gravity waves? What are they? Can you actually surf them? Or is this just a dream, a cosmic fantasy? You'll hear about ripples in space itself. You'll learn about black holes colliding billions of light years away. You'll discover how scientists detect these waves using lasers and mirrors. And you'll imagine what it would be like to ride a wave through the fabric of space and time itself. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now, let's begin. Chapter 1. What are gravity waves? Ripples in space and time. Gravity waves are not like ocean waves. They're not like sound waves. They're not like light waves. They're something completely different. They're ripples in space and time itself. They're distortions in the fabric of the universe. They're waves that travel through nothing and everything at the same time. Imagine space is like a blanket, a huge, invisible blanket that stretches across the entire universe. When something heavy sits on this blanket, it creates a dip, a curve, a bend. That's what gravity does. Massive objects like stars and planets create curves in space. They bend the fabric of the universe around them. Now imagine two heavy objects moving, two black holes, for example. They orbit each other. They spin around and around. As they move, they create ripples in the blanket. These ripples spread outward. They travel through space. They carry energy. They carry information. These are gravity waves. Gravitational waves, ripples in the fabric of space and time. Gravity waves were predicted by Albert Einstein over 100 years ago. In 1915, Einstein published his theory of general relativity. This theory changed how we understand gravity. Before Einstein, we thought gravity was a force, like magnetism, something that pulls objects together. But Einstein showed that gravity is actually the bending of space and time. Massive objects don't pull on each other. They bend space around them, and objects follow these curves. That's why planets orbit stars. That's why moons orbit planets. They're following the curves in space. Einstein published this theory in November 1915. He had been working on it for years. The theory was so revolutionary that it took time for other scientists to understand it. Some didn't believe it at first. But over the years, every test has confirmed that Einstein was right. His theory has passed every single test. Until gravity waves, that is. Gravity waves were the last prediction of general relativity that hadn't been directly detected. Now they have been. And Einstein's theory has passed this final test too. Einstein's theory also predicted that when massive objects move, they should create waves, ripples in space and time. But Einstein thought these waves would be too weak to ever detect. He thought we would never be able to measure them. They would be so tiny, so faint, that they would be invisible. But Einstein was wrong. Not about the waves existing, they do exist, but about us never detecting them. Because in 2015, scientists did something amazing. They detected gravity waves for the first time. The waves they detected came from two black holes colliding. These black holes were about 1.3 billion light-years away. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. So these black holes were incredibly far away. But when they collided, they created ripples. Ripples that traveled through space for 1.3 billion years. Ripples that reached Earth. Ripples that scientists could detect. Gravity waves travel at the speed of light. That's fast, very fast. About 300,000 kilometers per second. Nothing travels faster than light, and gravity waves travel at exactly that speed. They're the fastest ripples in the universe. When two black holes collide, the waves they create spread outward in all directions, like ripples in a pond. But these ripples travel through space itself, through the fabric of the universe. Gravity waves are incredibly weak. Even the strongest gravity waves are tiny. When they pass through Earth, they stretch and squeeze space by less than the width of a proton. A proton is one of the particles that make up an atom. It's incredibly small, about 1,000,000 times smaller than a grain of sand. So gravity waves stretch space by less than that. It's almost nothing. But scientists can still detect it, with incredibly sensitive instruments, with lasers and mirrors, with technology that didn't exist when Einstein was alive. To put this in perspective, if you stretched the entire 4-kilometer LIGO arm by the width of a proton, that would be like stretching the distance from Earth to the nearest star by the width of a human hair. That's how tiny the change is. But LIGO can detect it. It's one of the most precise measurements humans have ever made. Gravity waves carry energy. When two black holes collide, they release enormous amounts of energy. Most of this energy goes into creating gravity waves. These waves carry the energy away. They spread it across the universe, like throwing a stone into a pond. The ripples carry energy away from where the stone landed. Gravity waves do the same thing. They carry energy away from colliding black holes, away from merging neutron stars, away from any massive object that moves. Gravity waves also carry information. They tell us about the objects that created them, about how massive they were, about how fast they were moving, about how they collided. By studying gravity waves, scientists can learn about events that happened billions of years ago, events that are too far away to see with telescopes, events that happened before humans existed. Gravity waves are like cosmic messengers. They bring us news from across the universe. Gravity waves are not constant. They're not always there. They're created by specific events, by massive objects moving, by black holes colliding, by neutron stars merging, by supernovas exploding. These events create bursts of gravity waves, short pulses, brief ripples. Then they fade away. The waves continue traveling, but they get weaker as they spread out, like ripples in a pond, getting smaller as they move away from where the stone landed. The first gravity wave detection was called GW 150914. The GW stands for gravitational wave. The numbers are the date it was detected, September 14, 2015. This was a historic moment, the first time humans detected ripples in space and time, the first time we proved that Einstein was right about gravity waves existing. It was like hearing the universe for the first time, like discovering a new sense, a new way to explore the cosmos. Scientists from the LIGO team spent months checking this signal. They wanted to be absolutely sure. According to Dr. Kip Thorne, one of the founders of LIGO, they had to rule out every possible source of noise. They checked for earthquakes. They checked for trucks driving by. They checked for everything. Only after all those checks did they know it was real. A real ripple from two black holes colliding billions of years ago. The two black holes that created GW 150914 were massive. One was about 36 times the mass of our Sun. The other was about 29 times the mass of our Sun. Together, they had about 65 times the mass of our Sun. But when they merged, the final black hole had only about 62 times the mass of our Sun. What happened to the other three solar masses? They were converted into energy, into gravity waves. That energy traveled across the universe. It reached Earth, and scientists detected it. Scientists calculated that these black holes were spinning. One was spinning at about 70% of the maximum possible speed. The other was spinning at about 60%. When black holes spin, they create stronger gravity waves. The spin also affects how they merge. Scientists can learn all of this from the gravity wave signal. It's like reading a cosmic fingerprint. Every detail tells a story about what happened 1.3 billion years ago. This conversion of mass into energy follows Einstein's famous equation: E equals mc squared. Energy equals mass times the speed of light squared. This equation shows that mass and energy are the same thing. They can be converted into each other. When the two black holes merged, some of their mass became energy. Energy in the form of gravity waves. Physicists calculated that in that final second, the black holes released more energy than all the stars in the observable universe combined. That's how powerful it was. In just 1 second. More energy than billions of galaxies, all converted from mass into ripples in space and time. This is the most powerful conversion of mass to energy we've ever detected. More powerful than a supernova, more powerful than anything else in the universe. Gravity waves are not just from black holes. They can come from many sources. Neutron stars are another source. Neutron stars are what's left when a massive star explodes. They're incredibly dense. A teaspoon of neutron star material would weigh billions of tons on Earth. That's heavier than Mount Everest, all in one tiny teaspoon. When two neutron stars orbit each other and merge, they create gravity waves. Scientists have detected these too. Researchers have found that neutron star material is so dense that if you dropped a marshmallow on a neutron star, it would hit with the force of a nuclear bomb. That's how extreme these objects are. And when two of them merge, they create ripples that travel across the universe. Supernovas can also create gravity waves. When a massive star explodes, it creates ripples in space. These ripples are weaker than those from black hole mergers, but they still exist. They still travel through space. They still carry information about the explosion.
Even the Big Bang might have created gravity waves. The universe began with an enormous explosion. This explosion would have created ripples in space and time. these ripples would still be traveling through the universe today. They would be incredibly weak, incredibly old, but they might still be detectable. Scientists are looking for them. They're called primordial gravity waves, waves from the beginning of time itself. Gravity waves are everywhere. They're passing through you right now. As you rest, gravity waves are flowing through your body, through Earth, through everything. They're so weak that you can't feel them. You can't detect them with your senses. But they're there, constant reminders that the universe is alive, that space itself is moving, that time itself is rippling. If you could see gravity waves, the universe would look different. Space would be constantly rippling, constantly moving, like the surface of a pond on a windy day. But we can't see them. We can only detect them with special instruments, with technology that measures tiny changes in distance, changes so small they're almost impossible to imagine. Gravity waves are one of the most amazing discoveries in science. They prove that space and time are not fixed. They're flexible. They can bend. They can ripple. They can wave. The universe is not a static stage. It's a dynamic, living thing. And gravity waves are its heartbeat, its pulse, its rhythm. Remember that gravity waves are all around you right now. They're passing through you. They're connecting you to events billions of light years away, to black holes colliding, to stars exploding, to the birth of the universe itself. You are part of this cosmic dance, part of these ripples in space and time, part of something bigger than you can imagine. Scientists have discovered something amazing about gravity waves. They're not just passing through us, they're actually part of us. Researchers studying the origins of life have found that gravity waves might have played a role in creating the elements we're made of. When neutron stars merge, they create heavy elements like iodine and bromine. These are essential for human biology. Without gravity waves carrying energy away from these mergers, the elements might not have formed the same way. So, in a very real sense, gravity waves helped create the building blocks of life itself. Physicists have also measured something incredible. When gravity waves pass through Earth, they cause the planet to stretch and compress. But the effect is so tiny that it's almost impossible to measure. Scientists calculated that if Earth was stretched by a gravity wave, the change would be about 10 to the negative 21 meters. That's 0.000000000001 meters. To put that in perspective, if you stretch the entire Earth by this amount, it would be like changing the distance from New York to Los Angeles by less than the width of a single atom. That's how tiny these effects are. But LIGO can still detect them. It's one of the most precise measurements ever made. Recent research has revealed something surprising about gravity waves. Scientists using pulsar timing arrays have detected a background hum of gravity waves. This isn't from a single event, it's from millions of supermassive black holes throughout the universe, all orbiting each other, all creating waves, all adding together. Like standing in a forest and hearing all the birds at once. But instead of birds, it's black holes, and instead of sound, it's ripples in space and time. This discovery was announced in 2023 by teams from around the world. The North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, was one of the teams. They studied 67 pulsars for 15 years. They found that the timing of the pulses was changing in a way that could only be explained by gravity waves passing through. This was the first evidence of a gravitational wave background, a constant hum from the universe itself.
Dr. Maura McLaughlin, a professor of physics and astronomy, explained this discovery in simple terms. She said it's like hearing the universe's heartbeat, not from one event, but from all the events happening at once. Millions of supermassive black holes, all creating waves, all adding together, creating a background that's always there, always humming, always rippling through space. But here's something interesting. Some scientists thought this background might be from the Big Bang itself, primordial gravity waves from the beginning of time. But the research shows it's actually from supermassive black holes at the centers of galaxies, orbiting each other, creating waves. This doesn't mean primordial waves don't exist. They might, but we haven't detected them yet. That's what Lisa will look for, waves from the very beginning of the universe. There's also a common misconception about gravity waves. Some people think they're dangerous, that they could harm Earth or life on Earth. But research shows this isn't true. Even the strongest gravity waves are incredibly weak by the time they reach us. They stretch space by less than the width of a proton. Your body stretches and squeezes with space, but the effect is so tiny that you can't feel it. You can't detect it. It's completely harmless. Scientists have calculated that even if you were standing right next to a black hole merger, the gravity waves wouldn't hurt you. The black hole's gravity would be the problem, not the waves themselves. Chapter 2. How do we detect gravity waves? The amazing technology. Detecting gravity waves is incredibly difficult. They're so weak that even the strongest ones stretch space by less than the width of a proton. How do you measure something that small? How do you detect ripples in space itself? The answer is LIGO, the Laser Interferometer Gravitational Wave Observatory. It's one of the most sensitive instruments ever built. It can measure changes in distance smaller than 1/10,000th the width of a proton. LIGO works like this. Imagine you have two mirrors. They're very far apart, about 4 kilometers apart. That's about 2.5 miles. You shine a laser at both mirrors. The laser light bounces off the mirrors and comes back. You measure how long it takes the light to travel to each mirror and back. If the distances are exactly the same, the light waves from both paths will line up perfectly. They'll interfere with each other in a specific way. The laser light in LIGO actually bounces back and forth about 400 times before being measured. This makes the path much longer. Instead of traveling 4 kilometers, the light travels about 1,600 kilometers inside each arm. That's like traveling from New York to Florida and back, all inside a 4-kilometer tube. This makes the detector incredibly sensitive to tiny changes. Now imagine a gravity wave passes through. It stretches space in one direction and squeezes it in another. This changes the distance to one mirror slightly, just a tiny bit, less than the width of a proton. But it's enough. The light waves no longer line up perfectly. They interfere differently. Scientists can detect this change. They can see the gravity wave. LIGO has 2 observatories, one in Washington State, one in Louisiana. They're thousands of kilometers apart. This is important because if both detect the same signal at almost the same time, scientists know it's real. It's not just noise. It's not just a local disturbance. It's a gravity wave passing through Earth. The 2 detectors are about 3,000 kilometers apart. That's about 1,900 miles. When a gravity wave passes through, it reaches one detector first, then the other. The time difference tells scientists which direction the wave came from. It's like having two ears. Your brain uses the time difference between when sound reaches each ear to figure out where it came from. LIGO does the same thing with gravity waves. But instead of ears, it uses detectors thousands of kilometers apart. The LIGO detectors are L-shaped. Each arm is 4 kilometers long. That's about 2.5 miles. The laser light travels down each arm. It bounces off mirrors at the end, it comes back. The two beams meet in the middle. They interfere with each other. When a gravity wave passes through, it changes the length of one arm relative to the other. This changes how the light waves interfere. Scientists can detect this change. The mirrors in LIGO are incredibly smooth. If you enlarged one of these mirrors to the size of Earth, the biggest bump would be less than a centimeter high. They're that smooth. They're also incredibly reflective. They reflect 99.999% of the light that hits them. Almost perfect mirrors. This is necessary because the light bounces back and forth hundreds of times. It travels thousands of kilometers inside the detector. If the mirrors weren't perfect, too much light would be lost. The mirrors are made of fused silica. That's a special type of glass. It's incredibly pure. Scientists polish these mirrors for months. They use special techniques to make them perfectly smooth. The mirrors are also coated with special materials that make them super reflective. These coatings are only a few atoms thick, but they're crucial. Without them, the mirrors wouldn't reflect enough light, and LIGO wouldn't work. The laser in LIGO is incredibly powerful. It starts with a small laser, but it's amplified, it's made stronger. By the time it reaches the mirrors, it's about 100,000 times more powerful than a typical laser pointer. This powerful light is necessary to detect the tiny changes caused by gravity waves. The laser in LIGO is actually infrared light. You can't see it with your eyes. It has a wavelength of about 1,064 nanometers. That's about 1,000 times longer than visible light. Scientists use infrared because it's less affected by air molecules. Even though LIGO has an amazing vacuum, there are still a few molecules left. Infrared light passes through them more easily than visible light. This reduces noise, and noise is the enemy when you're trying to detect something as tiny as a gravity wave. LIGO is also incredibly isolated. It's built to avoid vibrations. Earth is constantly shaking, from earthquakes, from traffic, from people walking, from wind. All of these create vibrations. Vibrations that could mask gravity waves. So LIGO is built to be as still as possible. The mirrors hang from wires. They're isolated from the ground. They're protected from vibrations. They float, almost, suspended in vacuum chambers, protected from everything. The vacuum inside LIGO is better than the vacuum in space. There's almost no air, almost no particles. This is necessary because even air molecules can interfere with the laser light. They can scatter the light. They can create noise. So LIGO removes almost all the air. It creates a vacuum that's 1 trillion times better than the vacuum in space. To create this vacuum, scientists pump out the air for weeks. They remove 99.999% of all the air molecules. What's left is so empty that if you put a single grain of sand in there, it would be like having a huge crowd in an empty stadium. That's how empty it is. This extreme vacuum is necessary because even a few air molecules would scatter the laser light and create false signals.
Building LIGO took decades. Scientists started planning it in the 1980s. They built the first version in the 1990s. It ran for years, but
it didn't detect anything. The technology wasn't sensitive enough. So they upgraded it. They made it better. They improved the mirrors. They improved the lasers. They improved the isolation. They made it 10 times more sensitive. This new version, called Advanced LIGO, started running in 2015, and within days it detected its first gravity wave. The detection of GW150914 was a team effort. Over 1,000 scientists worked on it, from dozens of countries. They analyzed the data. They checked everything. They made sure it was real. It took months to confirm, but when they were sure, they announced it to the world, and the world celebrated. It was one of the greatest scientific discoveries of all time. Dr. David Reitz, the director of LIGO, said that when they first saw the signal, they couldn't believe it. It was too perfect, too clear. They thought it might be a test signal that someone had injected into the system. But after checking everything, they realized it was real. A real gravity wave from 1.3 billion years ago. The signal was so strong that it appeared in the data just 3 minutes after the black holes merged. Well, 3 minutes after the waves reached Earth anyway. The actual merger happened 1.3 billion years ago. LIGO isn't the only gravity wave detector. There's also Virgo. It's in Italy. It works the same way as LIGO. But having multiple detectors is important. It helps scientists confirm detections. It helps them figure out where the waves came from. It helps them learn more about the events that created them. Virgo is near Pisa, Italy. It's run by a collaboration of scientists from Italy and France. Virgo's arms are 3 kilometers long, slightly shorter than LIGO's 4-kilometer arms, but it still works. Having 3 detectors working together is even better than 2. With 3 detectors, scientists can pinpoint exactly where a gravity wave came from. They can create a map of the sky showing the direction. This helps telescopes know where to look. That's how they found the neutron star merger in 2017. LIGO and Virgo detected the gravity wave. They told telescopes where to look, and telescopes found the light. There's also Kagra in Japan. It's underground, in a mine. This protects it from vibrations even more. It's also cooled to very low temperatures, about -253 degrees Celsius. That's just 20 degrees above absolute zero, the coldest temperature possible. This reduces thermal noise, the random movements of atoms. These movements can create false signals. By cooling the detector, scientists reduce this noise. They make it more sensitive. Kagra is the first large-scale gravity wave detector built underground. Scientists chose this location because the mine is so deep that it blocks out most vibrations from the surface. Even earthquakes are dampened. This makes it one of the quietest places on Earth for detecting gravity waves. In the future, there will be LISA, the Laser Interferometer Space Antenna. It will be in space, 3 spacecraft flying in formation, millions of kilometers apart. They'll use lasers to measure distances between them. When a gravity wave passes, it will change these distances. LISA will be able to detect lower frequency waves, waves from different sources, waves that LIGO can't detect. LISA will be able to detect gravity waves from supermassive black holes. These are black holes millions or billions of times more massive than our Sun. They're at the centers of galaxies. When 2 galaxies merge, their black holes can orbit each other. They can create gravity waves. But these waves have lower frequencies. They take longer to pass. LIGO can't detect them, but LISA will be able to. Detecting gravity waves is like listening to the universe. Before LIGO, we could only see the universe. We could only observe it with light, with telescopes. But now we can also hear it. We can detect ripples in space and time. We can listen to black holes colliding, to stars exploding, to the universe itself vibrating. Gravity wave astronomy is a new field. It's only been around since 2015, but it's already changed how we understand the universe. It's given us a new way to explore, a new sense, a new window into the cosmos. The technology behind LIGO is amazing. It pushes the limits of what's possible. It measures distances smaller than anything else. It detects changes that are almost impossible to imagine. It's a testament to human ingenuity, to our ability to explore, to our curiosity about the universe. Consider LIGO for a moment. Think about those lasers, those mirrors, those 4-kilometer arms. Think about how they're detecting ripples in space itself. Right now, as you rest, LIGO is listening. It's waiting. It's ready to detect the next gravity wave, the next ripple from across the universe. The technology behind LIGO keeps getting better. Scientists are always improving it. They're always making it more sensitive. In 2023, LIGO started its 4th observing run, called O4. This run was more sensitive than ever before. Scientists expected to detect gravity waves almost every day. That's how much the technology has improved. From detecting one event in 2015 to potentially detecting hundreds per year, it's an incredible improvement. During the O4 run, LIGO and its partner detectors have already found many new events. As of early 2024, the total number of confirmed gravity wave detections has grown to over 90. But scientists think there are many more waiting to be analyzed. The data is so rich that it takes time to process everything. Each detection needs to be checked. Each signal needs to be verified. It's like having so many messages from the universe that you can't read them all at once. Dr. David Shoemaker, a senior research scientist at MIT, explained how the upgrades work. He said that improving LIGO is like tuning a musical instrument. You make small adjustments, you reduce noise, you improve sensitivity. Each improvement makes the detector better at hearing the universe. The latest upgrades made LIGO about 40% more sensitive than before. That might not sound like much, but in science, small improvements can make huge differences. A 40% improvement means LIGO can now detect events from 40% farther away. And since volume increases with distance cubed, that means LIGO can now see about 2.7 times more of the universe. That's a lot more black holes, a lot more neutron stars, a lot more cosmic events to discover. The mirrors in LIGO are getting better too. Scientists have developed new coating techniques. They've found ways to make mirrors even more reflective, even smoother. The latest mirrors reflect 99.999% of the light. That might not sound much better than before, but when light bounces back and forth 400 times, even tiny improvements matter. A little bit more reflection means a lot more light, and more light means better detection. Scientists are also working on reducing quantum noise. This is noise that comes from the quantum nature of light itself. Even light has uncertainty. Even photons have randomness. This creates noise that can mask gravity waves. But researchers have found ways to reduce this noise. They use something called squeezed light. This is light that's been specially prepared to have less quantum uncertainty. It sounds like science fiction, but it's real, and it's helping LIGO detect even weaker signals.
There's also something called the quantum limit. This is the absolute limit of how sensitive a detector can be. It's set by the laws of quantum mechanics, the laws that govern the smallest particles. Scientists thought LIGO would hit this limit, that it couldn't get any better. But recent research shows that maybe it can. Maybe there are ways to push beyond the quantum limit, to make detectors even more sensitive. It's still theoretical, but it's exciting. It means the future might be even brighter than we thought. Kagra, the Japanese detector, has its own innovations. It's built underground in a mine. This protects it from vibrations. But it's also cooled to incredibly low temperatures, about -253 degrees Celsius. That's just 20 degrees above absolute zero. At these temperatures, atoms move very slowly. This reduces thermal noise, the random movements of atoms that can create false signals. By cooling the mirrors, scientists reduce this noise. They make the detector more sensitive. It's like making everything very still, very quiet. So quiet that even the tiniest ripples can be heard. Kagra also uses sapphire mirrors instead of fused silica. Sapphire is a crystal. It's harder, it's more stable. At very low temperatures, it works better than glass. This is another innovation, another way to improve detection. Scientists are always finding new ways to make things better, new materials, new techniques, new ideas. Virgo, the European detector, has also been upgraded. Its arms are 3 kilometers long, slightly shorter than LIGO's 4-kilometer arms. But it still works. And having 3 detectors working together is powerful. With 3 detectors, scientists can triangulate. They can figure out exactly where a gravity wave came from. They can create a map of the sky. This helps telescopes know where to look. It's like having 3 ears instead of 2. You can hear better. You can locate sounds more precisely. The collaboration between LIGO, Virgo, and Kagra is amazing. Scientists from dozens of countries work together. They share data. They analyze signals together. They confirm each other's discoveries. It's international cooperation at its best, all working toward the same goal: understanding the universe, hearing its ripples, listening to its stories. There are also plans for new detection methods. Scientists are exploring using atomic clocks. These are incredibly precise clocks, so precise that they can measure tiny changes in time. And gravity waves affect time. They stretch and squeeze time just like they stretch and squeeze space. So, atomic clocks might be able to detect gravity waves. It's a different approach, a different way to listen to the universe. Another idea is using photometric surveys. These are telescopes that measure the brightness of stars very precisely. If a gravity wave passes through, it might change the positions of stars slightly. This could change how bright they appear. By monitoring millions of stars, scientists might be able to detect these tiny changes. It's like watching the entire sky at once, looking for ripples in the pattern of starlight. These new methods are still being developed. They're experimental, but they show that scientists are creative. They're always thinking of new ways to explore, new ways to listen, new ways to understand the universe. Chapter 3. What creates gravity waves? Cosmic events that ripple space. Gravity waves are created by massive objects moving, but not just any movement. They need to accelerate, to change speed, to change direction. When objects move in circles, or when they collide, they create gravity waves. The more massive the objects and the faster they move, the stronger the waves. The strongest gravity waves come from black holes. Black holes are the most massive objects in the universe. They're created when massive stars die. When a star runs out of fuel, it collapses. If it's massive enough, it collapses into a black hole, a point of infinite density, a place where gravity is so strong that nothing can escape, not even light. Black holes come in different sizes. Stellar black holes are about 10 to 100 times the mass of our Sun. They're created when massive stars explode. Supermassive black holes are millions or billions of times more massive than our Sun. They're at the centers of galaxies. Our own galaxy, the Milky Way, has a supermassive black hole at its center. It's about 4 million times the mass of our Sun. Scientists call it Sagittarius A star. It's about 26,000 light-years away from us. That's far enough that we're safe, but close enough that we can study it. Astronomers have watched stars orbit around it. They move so fast that they complete an orbit in just 16 years. That tells us how massive the black hole is and how strong its gravity is. When two black holes orbit each other, they create gravity waves. As they orbit, they lose energy. This energy goes into creating gravity waves. The waves carry the energy away. The black holes move closer together. They orbit faster. They create stronger waves. This continues for millions or billions of years, until finally they merge. They become one black hole, and in that final moment, they create the strongest gravity waves of all. The first gravity wave detection, GW 150914, came from two stellar black holes merging. One was 36 times the mass of our Sun, the other was 29 times the mass of our Sun. They orbited each other for billions of years, getting closer and closer, moving faster and faster, creating stronger and stronger waves, until they merged. In that final second, they created waves more powerful than all the stars in the observable universe combined. When black holes merge, they create a specific pattern of waves. The frequency increases. It gets higher and higher, like a bird chirping, but faster, much faster. This is called a chirp. Scientists can hear this chirp in the gravity wave signal. It tells them that black holes are merging. It tells them how massive they are. It tells them how far away they are. The chirp from GW 150914 lasted only about 0.2 seconds. In that tiny fraction of a second, the frequency went from 35 cycles per second to 250 cycles per second. That's like a musical note going from very low to very high in less than a heartbeat. Scientists can convert this signal into sound. When you listen to it, it sounds like a bird chirping, a cosmic bird, chirping from 1.3 billion light-years away. Neutron stars also create gravity waves. Neutron stars are what's left when a massive star explodes. They're incredibly dense. A teaspoon of neutron star material would weigh billions of tons. They're about the size of a city, but they have the mass of our Sun. They're like giant atomic nuclei, made mostly of neutrons. When two neutron stars orbit each other, they create gravity waves, just like black holes. They lose energy, they move closer, they orbit faster, they create stronger waves. Eventually, they merge. But neutron star mergers are different from black hole mergers. They create light. They create gamma rays. They create elements like gold and platinum. They're cosmic forges, creating the heaviest elements in the universe. In 2017, LIGO detected a neutron star merger. It was called GW170817. This was special because telescopes also saw it. They saw the light, the gamma rays, the afterglow. This was the first time scientists detected both gravity waves and light from the same event. It was like seeing and hearing the universe. Astronomers from around the world worked together. Over 70 telescopes pointed at the same spot in the sky. They saw the explosion in visible light, in X-rays, in radio waves, in every type of light we can detect. This event happened about 130 million light-years away. That's much closer than the first black hole detection. Close enough that we could see the light. Scientists learned that this single merger created about 200 Earth masses of gold. All the gold in your jewelry? It probably came from an event like this billions of years ago. The gamma ray burst from this merger was detected just 1.7 seconds after the gravity wave. That's incredibly fast. It means the gamma rays and gravity waves traveled at almost exactly the same speed. This confirmed one of Einstein's predictions, that gravity waves travel at the speed of light. Scientists had measured this before, but never with such precision. The fact that they arrived within 1.7 seconds of each other after traveling 130 million light-years proves that gravity waves travel at the speed of light, exactly as Einstein predicted. The neutron stars that merged were about 1.3 and 1.4 times the mass of our Sun. They orbited each other for millions of years, getting closer, moving faster, creating gravity waves, until they merged. In that moment, they created a black hole. They also created a kilonova, an explosion that creates heavy elements, gold, platinum, uranium. All the precious metals on Earth came from events like this, from neutron stars merging billions of years ago. Scientists calculated that these neutron stars were about 20 kilometers across. That's about the size of a city. But they had the mass of our Sun. Our Sun is about 1.4 million kilometers across. So these neutron stars were incredibly dense. They were packed into a space 70,000 times smaller than our Sun. When they merged, they created a black hole with about 2.7 times the mass of our Sun. The rest of the mass was converted into energy and heavy elements, elements that eventually became part of planets, part of Earth, part of you. Supernovas can also create gravity waves. When a massive star explodes, it collapses. The core collapses into a neutron star or black hole. The outer layers explode outward. This asymmetric explosion can create gravity waves. But these waves are weaker than those from black hole mergers. They're harder to detect. Scientists are still looking for them. The problem is that supernovas are rare. In our galaxy, a supernova happens about once every 50 years. And most of them are too far away or not asymmetric enough to create detectable gravity waves. But scientists keep watching. They know that when they do detect one, it will teach us a lot about how stars explode, about how the heaviest elements are created, about the final moments of a star's life. Binary star systems can create gravity waves too. When two stars orbit each other, they create ripples. But these ripples are very weak, too weak for LIGO to detect. But LISA, the space-based detector, might be able to detect them. It will be sensitive to lower frequency waves, waves from objects that orbit more slowly. Pulsars can also create gravity waves. Pulsars are neutron stars that spin very fast. They emit beams of radiation, like cosmic lighthouses. If a pulsar is not perfectly round, it will create gravity waves as it spins. These waves are continuous. They're always there. Scientists are looking for them. They're called continuous waves. The Big Bang might have created gravity waves too. When the universe began, it expanded incredibly fast. This expansion might have created ripples in space and time. These ripples would still be traveling through the universe today. They would be incredibly weak, incredibly old, but they might still be detectable. Scientists are looking for them. They're called primordial gravity waves, waves from the beginning of time itself.
Gravity waves from the Big Bang would tell us about the very beginning of the universe, about what happened in the first fraction of a second, about how the universe was born. They would be the oldest signals we could ever detect, older than light, older than anything else. The strength of gravity waves depends on several things: the mass of the objects creating them, the speed they're moving, the distance they are from us. The closer they are, the stronger the signal. The more massive they are, the stronger the signal. The faster they're moving, the stronger the signal. Gravity waves from stellar black holes are strong enough for LIGO to detect if they're within about 1 billion light-years. That's a huge distance. But the universe is even bigger. So LIGO can only detect a small fraction of the gravity waves in the universe. Most are too weak, too far away. But as technology improves, we'll be able to detect more. We'll be able to hear more of the universe. Gravity waves are like cosmic fingerprints. Each event creates a unique pattern. Scientists can read these patterns. They can learn about the objects that created them, about their masses, about their spins, about how they merged. Gravity waves are a new way to study the universe, a new tool, a new sense. Right now, all across the universe, events are creating gravity waves, black holes merging, neutron stars colliding, stars exploding, all creating ripples, all sending waves through space, waves that might reach Earth, waves that LIGO might detect. The universe is alive with these ripples, with these waves, with these cosmic messages. Scientists have discovered something surprising about black hole mergers. Not all black holes are the same size. Most of the black holes LIGO has detected are between 5 and 50 times the mass of our Sun. These are called stellar black holes. They form when massive stars die. But researchers have also found evidence of intermediate mass black holes. These are between 100 and 100,000 times the mass of our Sun. They're bigger than stellar black holes, but smaller than supermassive black holes. Scientists aren't sure how these form. They might be the result of many smaller black holes merging, or they might form in a different way. LIGO has detected a few events that might be intermediate mass black holes, but it's still not certain. More detections will help solve this mystery. There's also something called the mass gap. This is a range of masses where black holes seem to be rare, between about 50 and 120 times the mass of our Sun. Scientists aren't sure why. It might be because stars in this mass range explode differently. They might not form black holes at all, or they might form them in a way that's hard to detect. Recent research suggests that some of these black holes might exist, but they're just harder to find. As LIGO becomes more sensitive, it might detect more of them, and that will help scientists understand how black holes form. Scientists have also learned something amazing about black hole spins. When two black holes merge, they can spin. They can spin very fast, almost at the speed of light. The spin affects how they merge. It affects the gravity waves they create.
By studying the waves, scientists can measure the spins. They found that some black holes spin at almost the maximum possible speed. Others spin more slowly. Some don't spin much at all. This tells scientists about how the black holes formed, about their history, about what happened before they merged. Dr. Vicky Calogera, a professor of physics and astronomy, explained this in simple terms. She said that black hole spins are like fingerprints. They tell a story about how the black holes were born, a story about how they lived, a story about how they died. By reading these fingerprints, scientists can learn about the universe's history, about how black holes form and evolve. There's also something called the black hole recoil. When two black holes merge, the final black hole can get a kick. It can be sent flying through space at incredible speeds. Scientists have measured this for the first time. They found a black hole that was moving at about 1,500 kilometers per second. That's incredibly fast, fast enough to escape from most galaxies. This black hole is now wandering through space, alone, drifting through the cosmos. It's like a cosmic orphan, created by a merger, kicked out by the energy of that merger. This discovery helps scientists understand how black holes move, how they can escape from galaxies, how they can wander through the universe. Neutron star mergers are also fascinating. Scientists have learned that these mergers create more than just gold and platinum. They create many heavy elements. Elements like strontium, which is used in fireworks. Elements like europium, which is used in TV screens. Elements like neodymium, which is used in magnets. All created in the intense heat and pressure of a neutron star merger. All scattered into space. All eventually becoming part of planets, part of Earth, part of you. Researchers have also found that neutron star mergers might create something called a magnetar. This is a neutron star with an incredibly strong magnetic field, billions of times stronger than Earth's magnetic field. These magnetars can create gamma-ray bursts, incredibly powerful explosions of light. Scientists think that some of the gamma-ray bursts we see might be from magnetars created in neutron star mergers. It's like the merger creates a new object, a new cosmic phenomenon, one that continues to affect the universe long after the merger is over. There's also something called a kilonova. This is the explosion that happens when neutron stars merge. It's different from a supernova. It's brighter in some ways, but shorter. It lasts only days or weeks. But in that time, it creates enormous amounts of heavy elements. Scientists have calculated that a single kilonova can create more gold than exists in the entire Earth, all in just a few days, all scattered into space, all eventually becoming part of new stars, new planets, new life. But here's something interesting. Not all neutron star mergers create the same elements. Some create more gold, others create more platinum. It depends on the masses of the neutron stars. It depends on how they merge. Scientists are still learning about this. Each new detection teaches them something new. Each new merger reveals new secrets about how the universe creates heavy elements. Supernovas are also important sources of gravity waves, but they're harder to detect. Most supernovas are too far away or not asymmetric enough. But scientists keep looking. They know that when they do detect one, it will be amazing. It will tell them about how stars explode, about how the heaviest elements are created, about the final moments of a star's life. There's also something called a core collapse supernova. This happens when a massive star runs out of fuel. The core collapses. It can collapse into a neutron star or black hole. The outer layers explode outward. If this explosion is not perfectly symmetric, it creates gravity waves. Scientists have been looking for these for years. They haven't found one yet, but they're getting closer. As detectors become more sensitive, they'll be able to detect weaker signals. Signals from supernovas, signals from the death of stars.
Scientists have also discovered something about binary systems. Not all binary systems are the same. Some have two black holes. Others have two neutron stars. Some have one of each, a black hole and a neutron star. These are called mixed binaries. LIGO has detected a few of these. They're interesting because they behave differently. The black hole can tear apart the neutron star. It can create a different kind of merger, a different kind of gravity wave. Scientists are still learning about these. Each detection is a new discovery. Each merger reveals new physics. There's also something called hierarchical mergers. This is when black holes merge multiple times. First, two small black holes merge. Then the resulting black hole merges with another, and so on. This can create larger and larger black holes. Scientists think this might be how intermediate mass black holes form. Through multiple mergers, through building up mass over time. It's like cosmic evolution. Black holes growing, merging, growing again, creating a hierarchy of sizes. Recent research has also revealed something about the rate of mergers. Scientists have calculated how often black holes merge in the universe. They estimate that in a volume of space the size of 1 billion light-years cubed, there might be one merger every few years. That might not sound like much, but the universe is huge, so there are mergers happening all the time, all across the universe, all creating gravity waves, all sending ripples through space. Scientists have also found that the rate might be higher than they thought. Early estimates suggested maybe one merger per year in the observable universe, but recent data suggests it might be more, maybe several per year, maybe even more. As LIGO detects more events, scientists will get better estimates. They'll learn more about how common these mergers are, and that will help them understand the universe better. There's also something called the stochastic background. This is the combined signal from all the mergers in the universe, all the black holes merging, all the neutron stars colliding, all adding together, creating a constant hum, a background noise of gravity waves. LIGO can't detect this yet. The individual events are too weak. But in the future, with more sensitive detectors, scientists might be able to. They might be able to hear the combined sound of all the mergers, the universe's gravitational wave background, a constant reminder that the cosmos is alive, that it's constantly merging, constantly rippling, constantly changing. Chapter 4. Why can't we surf gravity waves? The physics of riding space. Now we come to the big question. Can you actually surf a gravity wave? Can you ride a ripple through space and time? The answer is complicated, but mostly it's no. You can't surf gravity waves the way you surf ocean waves. But let's explore why. Let's understand the physics. Let's imagine what it would be like if you could. Ocean waves work because they're disturbances in water. Water is a medium. It has substance. It has mass. When you surf an ocean wave, you're riding on the water. The water pushes you up. Gravity pulls you down. You balance between these forces. You ride the wave. But gravity waves are different. They're not disturbances in a medium. They're disturbances in space itself. They're ripples in the fabric of the universe. There's nothing to ride on. There's no surface. There's no medium. Space itself is stretching and squeezing, but you're part of space, so you stretch and squeeze too. You can't ride something you're part of. When a gravity wave passes through you, it doesn't push you. It doesn't lift you. It stretches you. In one direction, you get longer. In the other direction, you get shorter. Then it reverses. You get shorter in the first direction and longer in the second. You oscillate. You vibrate. But you don't move through space. Space moves through you, and you move with it. When a gravity wave passes through you, it doesn't push you. It doesn't lift you. It stretches you. In one direction, you get longer. In the other direction, you get shorter. Then it reverses. You get shorter in the first direction and longer in the second. You oscillate. You vibrate. But you don't move through space. Space moves through you, and you move with it.
This stretching and squeezing is incredibly tiny. Even the strongest gravity waves stretch space by less than the width of a proton. So if a gravity wave passed through you, you would stretch by less than the width of a proton. You wouldn't notice it. You couldn't feel it. It's too small. Your body is made of atoms. Atoms are much bigger than protons. So this tiny stretching wouldn't affect you at all. But let's imagine. What if gravity waves were stronger? What if they stretched space by a noticeable amount? What if you could feel them? What would that be like? If a gravity wave stretched you by even 1%, it would be dangerous. Your body would be pulled apart. Your atoms would be separated. You wouldn't survive. But let's imagine you could survive. What would it feel like? Scientists have calculated that if you were near a merging black hole, the gravity waves would be strong enough to stretch you by much more than 1%. They could stretch you by 10%, or 50%, or even 100%. That would double your length. You'd be twice as tall, but also half as wide. Your body would be completely deformed. You wouldn't survive. But even if you could, it wouldn't be like surfing. You'd just be stretched and squeezed over and over, like being in a cosmic washing machine. Not fun at all. It would feel like being stretched, like being pulled in two directions at once, like your body is being deformed. It wouldn't be pleasant. It would be uncomfortable, maybe painful. But it wouldn't be like surfing. You wouldn't be moving through space. You would be staying in the same place, but your shape would be changing. Now, could you use gravity waves to travel? Could you ride them from one place to another? The answer is still no. Gravity waves don't carry matter. They carry energy, but they don't push objects through space. They just stretch and squeeze space itself. However, there's a theoretical possibility. If you could create gravity waves artificially, and if you could make them strong enough, you might be able to use them to travel. This is the idea behind warp drives, science fiction devices that bend space to travel faster than light. A warp drive would create a bubble of space around a spacecraft. The space in front would be compressed. The space behind would be expanded. The spacecraft would stay still inside the bubble, but the bubble itself would move through space, faster than light, at least in theory. But this is just theory. We don't know if it's possible. We don't know if we could create such strong gravity waves. We don't know if we could control them. We don't know if warp drives are even possible. But it's fun to imagine. Physicists have calculated that to create a warp bubble big enough for a small spacecraft, you would need more energy than exists in the entire observable universe. That's how much energy it would take. So while it's theoretically possible, according to Einstein's equations,
It's practically impossible with anything we know about physics. But some scientists are still working on it. They're trying to find ways to make it work with less energy. Maybe one day. Who knows? Another way to think about surfing gravity waves is to imagine riding on an object that's creating them, like two black holes orbiting each other. Could you orbit with them? Could you ride along as they create waves? The problem is that black holes are dangerous. Their gravity is incredibly strong. If you got too close, you would be torn apart. The tidal forces would stretch you. You would be spaghettified. That's the technical term. Spaghettified. Your body would be stretched into a long, thin shape, like spaghetti. You wouldn't survive. For a stellar black hole, the spaghettification would happen when you're about 600 kilometers away. That's the point of no return, the event horizon. Once you cross it, you can't escape. But even before that, the tidal forces would start stretching you. Your feet would feel stronger gravity than your head. You'd be pulled apart. For a supermassive black hole, the event horizon is much farther out. But the tidal forces are weaker, so you might actually survive crossing the event horizon. But you still couldn't escape, and you'd eventually be pulled into the black hole anyway. But let's imagine you could survive. What would it be like to orbit two merging black holes? You would be moving very fast, almost at the speed of light. You would experience time differently. Time would slow down for you. From your perspective, the merger would happen quickly. From Earth's perspective, it would take much longer. You would also experience the gravity waves directly. As the black holes orbit, space around you would ripple. You would stretch and squeeze. You would feel the waves. But again, you wouldn't be surfing them. You would be experiencing them. You would be part of them. There's another way to think about this. What if you could surf on the energy of gravity waves? What if you could extract energy from them? Could you use them to power something? Gravity waves do carry energy. When two black holes merge, they release enormous amounts of energy in the form of gravity waves. But this energy is spread out. It's diluted across the entire universe. By the time it reaches Earth, it's incredibly weak. Too weak to be useful. To extract energy from gravity waves, you would need to capture them. But they pass through everything. They don't interact with matter much. They just stretch and squeeze space. So there's nothing to capture, nothing to collect. The energy just passes through. However, in theory, if you could create a device that responds to the stretching and squeezing, you might be able to extract some energy. But it would be tiny, almost nothing, not enough to be useful. So the answer is mostly no. You can't surf gravity waves, not in the way you surf ocean waves. But that doesn't mean they're not amazing. They're still ripples in space and time. They're still cosmic messages. They're still one of the most incredible things in the universe. Gravity waves are like the universe's heartbeat. They're proof that space and time are alive, that they're dynamic, that they're constantly moving. Even if we can't surf them, we can detect them, we can study them, we can learn from them, and that's remarkable. Imagine what it would be like if you could feel gravity waves, if you could sense the ripples in space around you, if you could experience the universe vibrating. It would be like having a new sense, a sense that lets you feel the cosmos itself. Even though you can't surf gravity waves, you can still appreciate them. You can still marvel at them. You can still be amazed by ripples in space and time. Scientists have studied this question in detail. They've calculated exactly what would happen if you tried to surf a gravity wave. The results are clear. It's not possible.
Not with current physics, not with any physics we know about. But understanding why helps us understand gravity waves better. It helps us appreciate how different they are from ocean waves, how unique they are in the universe. Research has shown that gravity waves don't create a medium to ride on. Ocean waves move through water. Water has substance. It can push, it can lift, it can carry you along. But gravity waves move through space itself. Space isn't a substance. It's the fabric of the universe. When a gravity wave passes, space stretches and squeezes. But there's nothing to push against, nothing to ride on. You're part of space, so you stretch and squeeze with it. But you don't move through it. You don't ride on it. You just experience the distortion.
Physicists have also calculated the energy in gravity waves. Even the strongest waves carry very little energy by the time they reach us. A gravity wave from a black hole merger billions of light years away carries less energy than a single light bulb uses in a second. That's how weak they are. There's simply not enough energy to surf on, not enough to propel you, not enough to do anything useful. But here's something interesting. Some scientists have explored a theoretical concept called the surfing effect. This isn't about actually surfing gravity waves, it's about how electromagnetic waves might interact with gravity waves. The research shows that under very specific conditions, electromagnetic waves might experience changes when gravity waves pass through. But these effects are tiny, and they don't create a way to surf. They're just interesting physics, interesting interactions between different types of waves. Dr. Kip Thorne, one of the founders of LIGO, has explained this clearly. He said that gravity waves are like ripples in a pond, but you can't ride them. You can only watch them pass. You can only detect them. They're messengers, not transportation. They carry information, not matter. They tell us about the universe, but they don't take us anywhere. There's also something called the equivalence principle. This is a fundamental principle of physics. It says that all objects fall the same way in a gravitational field. It doesn't matter how heavy they are, they all accelerate the same. This principle also applies to gravity waves. When a gravity wave passes through, all objects experience the same distortion. You, Earth, the Moon, everything. All stretch and squeeze the same way. There's no difference, no way to use the wave to move relative to other objects, no way to surf. Scientists have also thought about whether you could use gravity waves for propulsion. The answer is still no, but the reasons are interesting. Gravity waves don't push, they don't pull, they just distort space. And since you're part of space, you distort with it, but you don't move through it. It's like being in a room that's getting bigger and smaller. You're in the room, so you get bigger and smaller with it, but you don't move to a different room. You just experience the change. However, there is one theoretical possibility: warp drives. These are science fiction devices that bend space to travel faster than light. They would create a bubble of space around a spacecraft. The space in front would be compressed. The space behind would be expanded. The spacecraft would stay still inside the bubble, but the bubble itself would move, faster than light, at least in theory. But here's the problem. Physicists have calculated that creating a warp bubble would require more energy than exists in the entire observable universe. That's how much energy it would take. So, while it's theoretically possible, according to Einstein's equations, it's practically impossible. But some scientists are still working on it. They're trying to find ways to make it work with less energy. Maybe one day, who knows? But for now, it's just a dream. A fascinating dream, but still a dream. There's also something called negative energy. This is energy that's less than zero. It sounds impossible, but according to quantum mechanics, it might exist. In very small amounts,
for very short times. Some scientists think negative energy might be needed for warp drives. It might allow space to be compressed in ways that normal energy can't. But we don't know if negative energy exists. We don't know if we could create it. We don't know if we could use it. It's all very theoretical, very speculative. But it's interesting to think about.
Scientists have also studied what would happen if you were very close to a black hole merger. Would the gravity waves be strong enough to surf then? The answer is still no, but for a different reason. The gravity waves would be stronger, much stronger. They might stretch you by 10% or 50% or even 100%. But that wouldn't be surfing. That would be being torn apart. Your body would be deformed. You wouldn't survive. And even if you could survive, you still wouldn't be surfing. You'd just be experiencing extreme distortion, extreme stretching and squeezing. Not fun at all. There's also the problem of the black hole's gravity itself. If you're close enough to a black hole merger to feel strong gravity waves, you're also close enough to feel the black hole's gravity. And that gravity would be incredibly strong. It would pull you in. It would spaghettify you. It would kill you. Long before the gravity waves could do anything interesting. So even in the most extreme scenario, surfing isn't possible. The physics just doesn't work that way. But here's something to think about. Even though we can't surf gravity waves, we can still appreciate them. We can still marvel at them. We can still be amazed by the fact that space itself can ripple, that the universe can wave, that we can detect these ripples from billions of light years away. That's pretty amazing, even if we can't surf them. Chapter 5. The History of Gravity Waves, from Einstein to today. The story of gravity waves begins with Albert Einstein. In 1915, he published his theory of general relativity. This theory changed everything. It showed that gravity is not a force. It's the bending of space and time. Massive objects create curves in space. Objects follow these curves. That's why planets orbit stars. That's why apples fall from trees. Einstein's equations also predicted something else. They predicted that when massive objects move, they should create waves, ripples in space and time. But Einstein thought these waves would be too weak to ever detect. He thought they would be theoretical, interesting to think about, but impossible to measure. For decades, scientists debated whether gravity waves were real. Some thought they were just mathematical artifacts, tricks of the equations, not real physical things. Others thought they were real, but undetectable, too weak, too small, too impossible. Even Einstein himself changed his mind. At first, he thought gravity waves were real. Then he published a paper saying they might not exist. Then he changed his mind again. He wrote another paper saying they do exist, but we'll never detect them. Scientists kept debating this for years. It wasn't until 2015 that we finally knew for sure. Einstein was right about them existing, but he was wrong about us never detecting them. In 1936, Einstein and a colleague wrote a paper claiming that gravity waves don't exist. They thought they had found a mathematical error in the theory, but the journal rejected the paper. The editor found an error in Einstein's math. Einstein was embarrassed. He withdrew the paper. A year later, he published a new paper saying gravity waves do exist, but he still thought we'll never detect them. He thought they would be too weak, too small, too impossible. It took 78 years to prove him wrong about that part.
In the 1950s, a physicist named Joseph Weber decided to try. He built the first gravity wave detector. It was a large aluminum cylinder, about 2 meters long, about 1 meter in diameter. He hung it from wires. He isolated it from vibrations. He attached sensors to detect if it vibrated. Weber's idea was that if a gravity wave passed through, it would stretch and squeeze the cylinder. This would make it vibrate. The sensors would detect this vibration. It was a simple idea, but it was the first attempt.
Weber claimed to have detected gravity waves, but other scientists couldn't reproduce his results. They built similar detectors, but they didn't detect anything. Most scientists concluded that Weber was wrong, that he was detecting noise, not gravity waves. But Weber's work inspired others. It showed that detecting gravity waves might be possible. It just needed better technology, more sensitive instruments, better isolation from vibrations. Weber's detector wasn't sensitive enough. It would have needed to be about 1 billion times more sensitive to actually detect gravity waves. But his idea was right. His approach was right. He just needed technology that didn't exist yet. Today, we honor Weber as a pioneer. He was the first to try, and trying is what matters. In the 1960s, scientists started thinking about using lasers. Lasers had just been invented. They were new technology, but they were perfect for measuring tiny distances. If you could measure distances precisely enough, you could detect gravity waves. The idea was to use interferometry. This is a technique that uses the interference of light waves to measure distances. If 2 light waves meet, they can interfere with each other. They can add together or cancel each other out. This depends on how their waves line up, which depends on the distances they traveled. If you split a laser beam, send it down 2 paths, and then combine it again, you can measure tiny differences in the path lengths. This is how LIGO works. But in the 1960s, this was just an idea. The technology didn't exist yet. In the 1970s, scientists started building prototypes, small versions of what would become LIGO. They tested the technology. They improved it. They learned what worked and what didn't. It was slow progress, but it was progress. In the 1980s, scientists proposed building LIGO, a large-scale gravity wave detector, with 4-kilometer arms, with powerful lasers, with perfect mirrors. It would be expensive. It would take years to build. But it might work. It might detect gravity waves. Construction began in the 1990s. 2 sites were chosen, one in Washington State, one in Louisiana. They were far apart. This would help confirm detections. If both detected the same signal, it would be real, not just noise. The sites were chosen carefully. Scientists needed places that were quiet, away from cities, away from traffic, away from earthquakes. The Washington site is in Hanford. It's in the desert, very quiet. The Louisiana site is in Livingston. It's in a forest, also very quiet. Both sites are on government land. This made it easier to build such large structures. The construction cost about $620 million. That's a lot of money, but it was worth it. The discovery of gravity waves changed our understanding of the universe forever. The first version of LIGO was completed in 2002. It started running. Scientists watched, they waited, they analyzed data, but they didn't detect anything. The detector wasn't sensitive enough. Gravity waves were still too weak, too small, too impossible. The first LIGO ran from 2002 to 2010. That's 8 years.
In all that time, it didn't detect a single gravity wave. Scientists knew it wasn't sensitive enough, but they kept running it. They learned a lot. They learned how to reduce noise. They learned how to improve the technology. They learned what worked and what didn't. It was slow progress, but it was progress. In the 1980s, scientists proposed building LIGO, a large-scale gravity wave detector, with 4-kilometer arms, with powerful lasers, with perfect mirrors. It would be expensive. It would take years to build, but it might work. It might detect gravity waves. Construction began in the 1990s. 2 sites were chosen, one in Washington State, one in Louisiana. They were far apart. This would help confirm detections. If both detected the same signal, it would be real, not just noise. The sites were chosen carefully. Scientists needed places that were quiet, away from cities, away from traffic, away from earthquakes. The Washington site is in Hanford. It's in the desert, very quiet. The Louisiana site is in Livingston. It's in a forest, also very quiet. Both sites are on government land. This made it easier to build such large structures. The construction cost about $620 million. That's a lot of money, but it was worth it. The discovery of gravity waves changed our understanding of the universe forever. The first version of LIGO was completed in 2002. It started running. Scientists watched, they waited, they analyzed data, but they didn't detect anything. The detector wasn't sensitive enough. Gravity waves were still too weak, too small, too impossible. The first LIGO ran from 2002 to 2010. That's 8 years. In all that time, it didn't detect a single gravity wave. Scientists knew it wasn't sensitive enough, but they kept running it. They learned a lot. They learned how to reduce noise. They learned how to improve the technology. They learned what worked and what didn't. All of this knowledge went into building Advanced LIGO, the upgraded version that finally succeeded. Sometimes failure teaches you more than success. The first LIGO's failure was actually crucial. It taught scientists everything they needed to know to build a detector that would work. So, scientists upgraded LIGO. They made it better. They improved the mirrors. They improved the lasers. They improved the isolation. They made it 10 times more sensitive. This new version was called Advanced LIGO. It started running in 2015.
And then it happened. On September 14, 2015, LIGO detected its first gravity wave, GW 150914. 2 black holes merging, 1.3 billion light-years away. The signal was clear. It was real. It was historic. The timing was incredible. Advanced LIGO had just started running. It had been operating for less than 2 days when it detected this signal. Scientists couldn't believe their luck. They thought it would take months or years to detect the first gravity wave. But there it was, right away. Like the universe was waiting for us to be ready, waiting for us to finally listen. Scientists spent months checking. They analyzed the data. They made sure it wasn't noise. They made sure it was real. And when they were certain, they announced it to the world. On February 11, 2016, they held a press conference. They told the world that they had detected gravity waves, that Einstein was right, that ripples in space and time are real. The press conference was held at the National Press Club in Washington, D.C. Scientists from around the world gathered. They announced the discovery to the world. The news spread quickly. It was on the front page of newspapers. It was on TV. It was everywhere.
People were excited. This was one of the greatest scientific discoveries of all time. 3 of the founders of LIGO won the Nobel Prize in Physics in 2017 for this discovery: Rainer Weiss, Barry Barish, and Kip Thorne. They had worked on this for decades, and finally, they succeeded. The world celebrated. It was one of the greatest scientific discoveries of all time. It proved that gravity waves exist. It opened a new window into the universe. It started a new field of astronomy, gravity wave astronomy. Since then, LIGO has detected many more gravity waves, black holes merging, neutron stars colliding. Each detection teaches us something new. Each detection is a new discovery. Each detection is amazing. As of 2023, LIGO and its partner detectors have found over 90 confirmed gravity wave events. That's from just a few years of observations. Scientists estimate that there are thousands of these events happening every year in the universe. We're just now starting to hear them. Each one tells a story about massive objects colliding, about space rippling, about the universe doing something amazing. In 2017, LIGO detected a neutron star merger, GW1707. This was special because telescopes also saw it. They saw the light, the gamma rays. This was the first time scientists detected both gravity waves and light from the same event. It was like seeing and hearing the universe at the same time. The detection of gravity waves has changed astronomy. Before, we could only see the universe. We could only observe it with light. But now, we can also hear it. We can detect ripples in space and time. We can listen to black holes colliding, to stars exploding, to the universe itself vibrating. In 2017, LIGO detected a neutron star merger, GW1707. This was special because telescopes also saw it. They saw the light, the gamma rays. This was the first time scientists detected both gravity waves and light from the same event. It was like seeing and hearing the universe at the same time. The detection of gravity waves has changed astronomy. Before, we could only see the universe. We could only observe it with light. But now, we can also hear it. We can detect ripples in space and time. We can listen to black holes colliding, to stars exploding, to the universe itself vibrating. The future of gravity wave astronomy is bright. LIGO will keep improving. It will become more sensitive. It will detect more waves, from more sources, from farther away. LISA will launch in the 2030s. It will be in space. It will detect lower frequency waves, waves from supermassive black holes, waves from the early universe. It will open new windows into the cosmos. LISA will be huge. The 3 spacecraft will form a triangle. Each side will be 2.5 million kilometers long. That's about 6 times the distance from Earth to the Moon. All 3 spacecraft will fly together. They'll use lasers to measure the distances between them. When a gravity wave passes, it will change these distances. LISA will be able to detect waves that take hours or even days to pass, much longer than the seconds-long waves that LIGO detects. There are also plans for even larger detectors, on Earth, in space. They will be more sensitive. They will detect more waves. They will teach us more about the universe.
The story of gravity waves is still being written. Every detection is a new chapter. Every discovery is a new page. We're just beginning to explore this new way of seeing the universe, this new sense, this new window into the cosmos. Consider this story. Think about Einstein predicting gravity waves over 100 years ago. Think about scientists spending decades trying to detect them. Think about LIGO finally succeeding. Think about all the discoveries still to come. The story of gravity waves is a story of human curiosity, of persistence, of the desire to understand the universe. And it's a story that's still unfolding right now. The history of gravity waves is full of interesting moments, full of discoveries, full of setbacks, full of persistence. It's a story worth telling, a story worth remembering. After Einstein published his theory, other scientists started thinking about gravity waves. In 1918, Einstein himself published a paper calculating how much energy gravity waves would carry. He found that they would be incredibly weak, so weak that he thought we'd never detect them. But he was wrong about that part. We did detect them, eventually. In the 1920s and 1930s, scientists debated whether gravity waves were real. Some thought they were just mathematical artifacts, tricks of the equations, not real physical things. Others thought they were real, but undetectable. The debate continued for decades. It wasn't until the 1950s that someone actually tried to detect them. That someone was Joseph Weber. He was a physicist at the University of Maryland. He built the first gravity wave detector. It was called a Weber bar, a large aluminum cylinder. He hung it from wires. He isolated it from vibrations. He attached sensors to detect if it vibrated. His idea was simple. If a gravity wave passed through, it would stretch and squeeze the cylinder. This would make it vibrate. The sensors would detect this vibration. Weber claimed to have detected gravity waves, but other scientists couldn't reproduce his results. They built similar detectors, but they didn't detect anything. Most scientists concluded that Weber was wrong, that he was detecting noise, not gravity waves. But Weber's work was important. It showed that detecting gravity waves might be possible. It just needed better technology. Weber's detector wasn't sensitive enough. It would have needed to be 1 billion times more sensitive to actually detect gravity waves. But his idea was right. His approach was right. He just needed technology that didn't exist yet. Today, we honor Weber as a pioneer. He was the first to try, and trying is what matters. In the 1960s, scientists started thinking about lasers. Lasers had just been invented. They were new technology, but they were perfect for measuring tiny distances. If you could measure distances precisely enough, you could detect gravity waves. The idea was to use interferometry. This is a technique that uses the interference of light waves to measure distances. The first person to propose using interferometry for gravity wave detection was Rainer Weiss. He was a professor at MIT. In 1972, he wrote a paper describing how it could work. He proposed building a detector with kilometer-long arms, with lasers, with mirrors. It was a bold idea, but it was the right idea. It's the idea that LIGO is based on today. Weiss wasn't alone. Other scientists were also thinking about interferometry. In the 1970s, several groups started building prototypes, small versions of what would become LIGO. They tested the technology. They improved it. They learned what worked and what didn't. It was slow progress, but it was progress. One of the key figures was Kip Thorne. He was a professor at Caltech.
He became interested in gravity waves in the 1970s. He started working on the theory, on how to detect them, on what we might learn from them. He became one of the founders of LIGO, one of the people who made it happen.
Another key figure was Barry Barish. He was also at Caltech. He became the director of LIGO in the 1990s. He oversaw the construction. He made sure it got built. He made sure it worked. He was instrumental in making LIGO a reality. In the 1980s, scientists proposed building LIGO, a large-scale gravity wave detector, with 4-kilometer arms, with powerful lasers, with perfect mirrors. It would be expensive. It would take years to build, but it might work. It might detect gravity waves. The proposal was submitted to the National Science Foundation. It was a big ask, hundreds of millions of dollars, for something that might not work. But the foundation said yes. They funded it. They believed in the science. They believed it was worth the risk. Construction began in the 1990s. 2 sites were chosen, one in Washington State, one in Louisiana. They were far apart. This would help confirm detections. If both detected the same signal, it would be real, not just noise. The construction took years. It was complicated. It required precision. It required patience. But eventually, it was done. The first version of LIGO was completed in 2002. It started running. Scientists watched. They waited. They analyzed data. But they didn't detect anything. The detector wasn't sensitive enough. Gravity waves were still too weak, too small, too impossible. The first LIGO ran from 2002 to 2010. That's 8 years. In all that time, it didn't detect a single gravity wave. But that wasn't a failure. It was a learning experience. Scientists learned a lot. They learned how to reduce noise. They learned how to improve the technology. They learned what worked and what didn't. All of this knowledge went into building advanced LIGO, the upgraded version that finally succeeded. The upgrade took years. Scientists improved everything: the mirrors, the lasers, the isolation. They made it 10 times more sensitive. This new version was called Advanced LIGO. It started running in 2015. And then it happened. On September 14, 2015, LIGO detected its first gravity wave, GW15094, 2 black holes merging, 1.3 billion light-years away. The signal was clear. It was real. It was historic. The timing was incredible. Advanced LIGO had just started running. It had been operating for less than 2 days when it detected this signal. Scientists couldn't believe their luck. They thought it would take months or years to detect the first gravity wave. But there it was, right away, like the universe was waiting for us to be ready, waiting for us to finally listen. Scientists spent months checking. They analyzed the data. They made sure it wasn't noise. They made sure it was real. And when they were certain, they announced it to the world. On February 11, 2016, they held a press conference. They told the world that they had detected gravity waves, that Einstein was right, that ripples in space and time are real. The press conference was held at the National Press Club in Washington, D.C. Scientists from around the world gathered. They announced the discovery to the world. The news spread quickly. It was on the front page of newspapers. It was on TV. It was everywhere. People were excited. This was one of the greatest scientific discoveries of all time. 3 of the founders of LIGO won the Nobel Prize in Physics in 2017 for this discovery: Rainer Weiss,
Barry Barish and Kip Thorne. They had worked on this for decades, and finally, they succeeded. The Nobel Prize was recognition of their work, of their persistence, of their belief that gravity waves could be detected. Since then, LIGO has detected many more gravity waves, black holes merging, neutron stars colliding. Each detection teaches us something new. Each detection is a new discovery. Each detection is amazing.
The story of gravity waves is still being written. Every detection is a new chapter. Every discovery is a new page. We're just beginning to explore this new way of seeing the universe, this new sense, this new window into the cosmos. Chapter 6: The Future of Gravity Waves. What we might discover. The future of gravity wave astronomy is exciting. We've only just begun. We've detected a few dozen events, but there are billions more out there, waiting to be discovered, waiting to teach us about the universe. Scientists estimate that in our galaxy alone, there might be millions of black hole pairs orbiting each other, each one creating gravity waves, each one waiting to be detected. And our galaxy is just one of billions. The universe is full of these events. We're like someone who just learned to hear, and we're discovering that the universe is full of sounds we never knew existed. Astronomers have found evidence of black hole pairs in our galaxy. They've found stars orbiting invisible objects, objects that must be black holes. Some of these might be pairs, two black holes orbiting each other, creating gravity waves. But most are too far away or too small for LIGO to detect. As LIGO becomes more sensitive, it will detect more of these. Scientists think LIGO might detect one black hole merger per week in the future. That's 52 per year, just from our local region of the universe. The universe is full of these events. We're just starting to listen. As LIGO improves, it will detect more events, more black holes merging, more neutron stars colliding, more cosmic explosions. Each detection will teach us something new. Each detection will be a new discovery. LIGO will also detect events from farther away. As it becomes more sensitive, it can hear more of the universe. It can detect events that happened longer ago, events from when the universe was younger, events from the early cosmos. Scientists are also looking for continuous waves, waves that are always there, not just bursts. Pulsars that aren't perfectly round create continuous waves as they spin. Scientists are searching for these. They're like a constant hum, a background noise of gravity waves. If scientists find continuous waves, they could use them like cosmic lighthouses. They could navigate by them. They could use them to measure distances. They could use them to study the universe in new ways. LISA will launch in the 2030s. It will be a game changer. It will detect lower frequency waves, waves that LIGO can't hear, waves from supermassive black holes, waves from the early universe. When two galaxies merge, their supermassive black holes can orbit each other for millions of years. They create gravity waves. But these waves have low frequencies. They take a long time to pass. LIGO can't detect them, but LISA will be able to. LISA will also be able to detect waves from the Big Bang, primordial gravity waves, waves from the beginning of time itself. These would tell us about the very beginning of the universe, about what happened in the first fraction of a second, about how everything began. Scientists think the Big Bang created gravity waves during something called inflation. This was a period when the universe expanded incredibly fast, faster than the speed of light. This expansion would have created ripples in space and time. These ripples would still be traveling through the universe today, but they would be incredibly weak and incredibly old, almost 14 billion years old. LISA might be able to detect them. If it does, it would tell us about the very first moments of the universe, about how everything began. It would be like hearing the birth cry of the cosmos itself. There are also plans for even larger detectors on Earth. Detectors with 10-kilometer arms or 40-kilometer arms, much larger than LIGO, much more sensitive. They would detect even more events, even weaker waves, even farther away.
Scientists in Europe are planning a detector called the Einstein telescope. It would have 10-kilometer arms, 3 of them, arranged in a triangle. It would be 10 times more sensitive than LIGO. It would detect events from 10 times farther away. That means it could see 1,000 times more of the universe, because volume increases with the cube of distance. Scientists in the United States are planning a similar detector, called Cosmic Explorer. It would have 40-kilometer arms, even more sensitive. These detectors are still in the planning stage, but if they're built, they will revolutionize gravity wave astronomy. They'll detect thousands of events per year, instead of dozens. There are also plans for detectors in space, not just LISA, but other missions, different designs, different capabilities. They would complement each other. They would work together. They would create a network, a web of gravity wave detectors, listening to the universe. Scientists are also thinking about using pulsar timing arrays. Pulsars are neutron stars that spin very fast. They emit beams of radiation, like cosmic lighthouses. They're incredibly regular. They pulse at precise intervals. If a gravity wave passes through, it would stretch and squeeze space. This would change the distances to pulsars slightly. It would change when their pulses arrive. Scientists can measure these tiny changes. They can detect gravity waves this way. Pulsar timing arrays are already detecting something, a background hum of gravity waves from supermassive black holes throughout the universe, all creating waves, all adding together, creating a constant background, a cosmic symphony. In 2023, scientists using pulsar timing arrays announced they had detected this background hum. It's like hearing all the supermassive black holes in the universe at once, millions of them, all creating waves, all adding together. It's not a single event. It's the combined sound of the entire universe, like standing in a forest and hearing all the birds at once. But instead of birds, it's black holes. And instead of sound, it's ripples in space and time. In the future, gravity wave astronomy might answer big questions. How do black holes form? How do they grow? How do galaxies merge? What happened in the Big Bang? These are fundamental questions, questions about the universe itself. Gravity waves might also help us understand dark matter. Dark matter is mysterious. We can't see it, we can't detect it directly, but we know it's there. It affects gravity. It might create gravity waves. If we can detect these waves, we might learn about dark matter. Gravity waves might also help us test Einstein's theory.
General relativity has been tested many times. It's always passed. But gravity waves provide a new way to test it. In extreme conditions, near black holes, during mergers. We might find that the theory needs to be modified. We might discover new physics. So far, every gravity wave detection has matched Einstein's predictions perfectly. The signals look exactly like what the theory says they should look like. This is amazing. Einstein's theory was created over 100 years ago, long before we had computers, long before we could simulate black hole mergers. But his math was so good that it still works, even in the most extreme conditions in the universe, near black holes, during collisions. Einstein's theory still works, but scientists keep testing it, because one day we might find something that doesn't match, and that would be even more exciting, because it would mean we've discovered new physics, physics beyond Einstein. The future is full of possibilities, full of discoveries waiting to happen, full of mysteries waiting to be solved. Gravity wave astronomy is just beginning. We're like explorers setting out into a new ocean. We don't know what we'll find, but we know it will be amazing.
As technology improves, we'll detect more events. We'll learn more about the universe. We'll answer more questions. We'll ask new questions. The journey is just beginning. Imagine the future of gravity wave astronomy. Imagine Lisa detecting waves from the Big Bang. Imagine larger detectors finding events from the edge of the observable universe. Imagine a network of detectors listening to the cosmos. The future is bright, full of discoveries, full of wonder, full of the unknown. The future of gravity wave astronomy is being written right now. Every day brings new discoveries, new insights, new questions. It's an exciting time to be alive, an exciting time to be curious about the universe. Lisa is scheduled to launch in 2035. That's still more than a decade away. But scientists are already preparing. They're testing the technology. They're building prototypes. They're making sure everything will work. Lisa will be a game changer. It will detect lower frequency waves, waves that LIGO can't hear, waves from supermassive black holes, waves from the early universe. Lisa will consist of 3 spacecraft. They'll form a triangle. Each side will be 2.5 million kilometers long. That's about 6 times the distance from Earth to the Moon. The spacecraft will fly in formation. They'll use lasers to measure the distances between them. When the gravity wave passes, it will change these distances. Lisa will be able to detect these changes. It will be able to hear waves that take hours or even days to pass, much longer than the seconds-long waves that LIGO detects. Scientists estimate that Lisa will detect thousands of events per year. Supermassive black holes merging, white dwarfs orbiting each other, all creating waves, all sending ripples through space. Lisa will hear them all. It will create a map of the universe's gravitational wave sources, a map that we can't create with light, a map that only gravity waves can show us. Lisa will also look for primordial gravity waves, waves from the Big Bang, waves from the very beginning of the universe. These would be incredibly weak, incredibly old, almost 14 billion years old. But Lisa might be able to detect them. If it does, it would tell us about the very first moments of the universe, about what happened in the first fraction of a second, about how everything began. There are also plans for even larger detectors on Earth.
The Einstein telescope is planned for Europe. It would have 10-kilometer arms, 3 of them, arranged in a triangle. It would be 10 times more sensitive than LIGO. It would detect events from 10 times farther away. That means it could see 1,000 times more of the universe, because volume increases with the cube of distance. The Einstein telescope would be built underground. This would protect it from vibrations. It would be quieter, more sensitive. It would be able to detect weaker signals, signals from farther away, signals from the early universe. Scientists in the United States are planning a similar detector, called Cosmic Explorer. It would have 40-kilometer arms, even longer than the Einstein telescope, even more sensitive. It would be able to detect events from the edge of the observable universe, events from when the universe was very young, events from billions of years ago. These detectors are still in the planning stage. They haven't been built yet. They might not be built for decades. But if they are built, they will revolutionize gravity wave astronomy. They'll detect thousands of events per year, instead of dozens. They'll create a detailed map of the universe's gravitational wave sources. They'll answer questions we haven't even thought of yet.
There are also plans for other detection methods. Scientists are exploring using atomic clocks. These are incredibly precise clocks, so precise that they can measure tiny changes in time. And gravity waves affect time. They stretch and squeeze time just like they stretch and squeeze space. So atomic clocks might be able to detect gravity waves. It's a different approach, a different way to listen to the universe. Another idea is using photometric surveys. These are telescopes that measure the brightness of stars very precisely. If a gravity wave passes through, it might change the positions of stars slightly. This could change how bright they appear. By monitoring millions of stars, scientists might be able to detect these tiny changes. It's like watching the entire sky at once, looking for ripples in the pattern of starlight. Scientists are also thinking about using quantum sensors. These are devices that use quantum mechanics to make incredibly precise measurements. They might be able to detect gravity waves in new ways, ways we haven't thought of yet. The future is full of possibilities, full of new ideas, full of new ways to explore. Pulsar timing arrays will also continue to improve. Scientists are finding more pulsars. They're monitoring them more precisely. They're getting better data. This will help them detect the gravitational wave background more clearly. They'll be able to map it. They'll be able to understand it better. They'll be able to learn from it. The gravitational wave background is fascinating. It's the combined signal from all the mergers in the universe, all the black holes merging, all the neutron stars colliding, all adding together, creating a constant hum, a background noise of gravity waves. Scientists have already detected hints of this, but in the future they'll detect it more clearly. They'll be able to study it in detail. They'll be able to learn from it. In the future, gravity wave astronomy might answer big questions. How do black holes form? How do they grow? How do galaxies merge? What happened in the Big Bang? These are fundamental questions, questions about the universe itself. Gravity waves might help answer them. Gravity waves might also help us understand dark matter. Dark matter is mysterious. We can't see it, we can't detect it directly. But we know it's there. It affects gravity. It might create gravity waves. If we can detect these waves, we might learn about dark matter. We might finally understand what it is. Gravity waves might also help us test Einstein's theory. General relativity has been tested many times. It's always passed.
But gravity waves provide a new way to test it. In extreme conditions, near black holes, during mergers, we might find that the theory needs to be modified. We might discover new physics, physics beyond Einstein. So far, every gravity wave detection has matched Einstein's predictions perfectly. The signals look exactly like what the theory says they should look like. This is amazing. Einstein's theory was created over 100 years ago, long before we had computers, long before we could simulate black hole mergers. But his math was so good that it still works, even in the most extreme conditions in the universe, near black holes, during collisions. Einstein's theory still works, but scientists keep testing it, because one day we might find something that doesn't match. And that would be even more exciting, because it would mean we've discovered new physics, physics beyond Einstein, physics we don't understand yet. That's what science is about: testing theories, finding limits, discovering new things. The future is full of possibilities, full of discoveries waiting to happen, full of mysteries waiting to be solved. Gravity wave astronomy is just beginning. We're like explorers setting out into a new ocean. We don't know what we'll find, but we know it will be amazing.
As technology improves, we'll detect more events. We'll learn more about the universe. We'll answer more questions. We'll ask new questions. The journey is just beginning, and it's going to be incredible. Wow, what a journey we've been on! We've explored gravity waves, ripples in space and time. We've learned how they're created, how they're detected, why we can't surf them. We've traveled from Einstein's predictions to LIGO's discoveries. We've imagined the future. We've learned that gravity waves are ripples in the fabric of the universe, that they're created by massive objects moving, that they travel at the speed of light, that they carry energy and information across the cosmos. We've learned about LIGO, the amazing technology that detects these waves, lasers and mirrors, 4-kilometer arms, incredible sensitivity, the ability to measure changes smaller than a proton. We've learned about the events that create gravity waves, black holes merging, neutron stars colliding, stars exploding, cosmic events that ripple space itself. We've learned why we can't surf gravity waves. They're not like ocean waves. They're ripples in space itself. There's nothing to ride on. But they're still amazing, still incredible, still one of the most fascinating things in the universe. We've learned about the history, from Einstein's predictions to LIGO's first detection, decades of work, thousands of scientists, all leading to that moment, that discovery, that proof that ripples in space and time are real. We've imagined the future, LISA detecting waves from supermassive black holes, larger detectors finding events from the edge of the universe, a network of detectors listening to the cosmos. The future is bright, full of discoveries, full of wonder. Gravity waves are happening right now. As you listen to this, black holes are merging, neutron stars are colliding, stars are exploding, all creating ripples, all sending waves through space, waves that might reach Earth, waves that LIGO might detect. Thank you for joining me on this journey. I hope you learned something new. I hope you learned about gravity waves. I hope you're curious to learn more. And I hope you'll keep exploring, Keep asking questions and keep discovering. Science is full of questions, and that's what makes it awesome. There's always more to learn, more to discover, more to explore. The universe is vast and mysterious, and we are just beginning to understand it. Gravity waves have been traveling through the universe for billions of years. They'll keep traveling for billions more, and we'll keep detecting them, learning from them, and being amazed by them. They're a constant reminder that we are part of something bigger, that space itself is alive, that the universe is constantly moving, constantly rippling, constantly amazing. I'm Sleepy, and this was your science story for today. Sweet dreams, and keep looking up at the stars. Remember, even though you can't see them or feel them, gravity waves are all around you. They're passing through you right now. Ripples in space and time. Cosmic messages from across the universe. That's pretty special. Good night.